Okay, what I'm going to talk about in this video is numerically solving ordinary differential equations in Python. In this case, we're talking about a boundary value problem. Okay, so for example, a steady state differential equation where you know the boundary conditions on either side on a 1D problem. How can we use Python to solve this? I'll use this example for heat diffusion. Okay, so let's take a look at the simplified heat diffusion equation. This is written here. If we look at this in one dimension in steady state, we can rearrange this to be a second order differential equation in X. So you can solve temperature as a position, in a function of position, and you can have a generation term. Okay, so this can easily be analytically solved. Okay, so an analytical solution to this, if you just integrate it twice, is a parabola. Okay, so an analytical solution is we take this curve, we plot it, and we have a parabola that describes the temperature from T1 to T2, and you could look at the analytical solution to get really cool information about how, the generation term or K affect the shape of this curve. Now, a numerical solution is when we now represent this solution not by an analytical expression which describes it at every point, but by the value at very specific, what we'll call nodes. Okay, so what we're going to do is solve this differential equation. You'll get the exact same information, but in this case, we know the solution for the temperature at given nodes. Okay, so you have a finite number of nodes. Now, if these nodes were infinitely close together, if this spacing delta x goes to 0, then this would be the analytical solution. Okay, so this is the limit of a numerical solution. Before you take a differential distance between the nodes. And the reason is there's a lot of, like we'll see here, a lot of problems where you can't get a analytical solution to a problem. So let's talk about how we can do this numerically. We need to set up a grid, and then we need to pass it the information to be able to output the temperature, which is our dependent variable, as a function of position, which is our independent variable, at the given nodes that we set up. Okay. So our answer is going to be an array of values, okay, at each position that we give it. So let's set this up. And so what we want to do is, option 1, you set up your node. This is a 1D problem where you know the temperature at one side, the temperature at the other side. We're going to label these nodes in Python. We count from 0. So 0 would be this node, 1 would be the temperature at this node, 2 would be the temperature at this node. And so there's in nodes or in plus 1 nodes because, there's 0 to in. So option 1 is you can set up a finite difference method. So we can represent our second order differential equation by a finite difference equation. This would be a central difference approximation. And you can set this up and solve at each node. Okay, so this is linear algebra. So you can set up a matrix and solve for all these different nodes simultaneously, manually. We can talk about this at a later point. But option 2, and this is the option that we're going to choose, is going to be use a boundary value problem solver in Python. Okay, so there's initial value problems and boundary value problems. In this case, we've got the two boundaries. So there's a boundary value problem, and there's built-in solvers in Python that we can use. The one we're going to use is called solve BVP for boundary value problem. So it's in the scipy library. The package is integrate, and then the function is solve BVP. And so what this takes is you need to set up your function. So we need to define a function f. Okay. And then we need to pass it the function we want to solve. This is our BC is going to be our boundary condition residuals. I'll explain what this is. We need to tell it our array of the independent variable. So in this case, the X array that we're going to solve. So this is going to be the array that we define, meaning all these different nodes. They can be as close as far apart as we want to get the accuracy of the solution. And then an initial guess. So all these solutions are iterative. So it needs to have some sort of initial guess to solve the problem. So this is initial guess. Okay, so if we pass it these 4 things, it'll automatically give us the solution. And so the output, if we pass it a derivative t as a function of x, it's going to output t as a function of x. So this is going to be the output, and it's going to be an array. This is the output, and it's an array of t values that correspond to each x value at one of these nodes, at each one of these nodes. Okay, so that's the idea. That's what we're going to solve. And there's only one tricky part that goes into this. And that is that numerical solvers don't like second order ODEs. Okay, so typically when we're solving these 1D problems, it's a boundary value problem. There's typically a second order differential equation because that's because of the nature of this problem, and you have two boundary conditions. So what we need to do is redefine this as a system of first order ODEs. Okay, and so it's pretty straightforward to redefine this. Maybe you remember from your calculus class. We just need to define a substitute variable. There's one, we'll make one up. So let's say we have some function p of x is what we're going to define. And let's call that dt dx. Okay, so if we define a new function p, which is just the first derivative, then what we can do is rewrite this as a system of equations. Okay, so our first equation is going to be dt dx equals p, and our second equation is going to be dp dx. Now, what is dp dx? Would be the derivative of this. Okay, so the derivative of this is the derivative of this. That's the second derivative. Okay, so we already know what that is. That's exactly what we defined. So this equals minus q generation, volumetric generation divided by k. Okay, so that's how you would turn this second order differential equation into a first order differential equation. You just need to redefine it. So in this case, it's just a little tricky because instead of passing it a function f, we're going to pass it a system. So you can pass it an array of functions, so multiple functions. So we're going to define it as two different rows, and we're going to pass each function. We're going to give it this function and this function. So the idea is this function that you're passing it, this is, we'll call dy dx. This is what it wants, okay? So it wants to know the function. Remember, we're inputting some function, and the functional form that this solver wants it in is f, where you input x and y. Okay, so in this case, x is the independent variable. So this, in our case, if this is dy dx, then x is our independent variable for this would be both for both systems. X is the independent variable. So x is going to be an array at the first node, the second node. Let me write this in block here. 0, 1, 2, all the way to node n. Okay, so these are the nodes. So this is going to be the x value at each node. Okay. And then our y is going to be what? So if this is f of xy is going to be dy dx, then y is the dependent variable for each one of these. So y for this equation is going to be t, and y for this equation is going to be p. Okay, so what you're going to solve is t is a function of x and p is a function of x as our output. So it's going to solve this differential equation and output t of x, and then this is going to output p of x, and we know p of x is the first derivative. So we automatically get the function and the first derivative from this solution. So y for our first set of equations is going to be t. So it's going to be t at 0. It's going to be an array. For example, t at position 1, t at position 2 is going to be an array all the way to t at node n plus 1, or yeah, node n. And the p output, this would be y for our second function. This is going to be dy dx for our second function is going to be dt dx, because p is dt dx. Okay, so this is going to be dt dx at x equals 0, dt dx at x equals 1, dt dx at x equals 2, and so on, all the way to dt dx at x equals n. Okay, so it's going to be the first derivative of each one of these points. Now, if you go in Python and you call the first element of y, the first element is y0, that's going to be this whole array. It's going to be all an array of the temperature values. And y element 1, the first element, is going to be the array of the first derivatives, which is the independent variable here. Now, the function we're trying to solve, okay, so dy dx equals some function, okay? So we got to look at that for each one of these. So this is y, let's just write this. This is y, x, this is y, well, I think the point here, this is y, x, and this is f, okay? So this is our functions. So the function, which is going to be what the derivative equals, in the first example, it's p, okay? So we know p is just dt dx. So this is an interesting one because dt dx is already defined as a dependent variable. So it's y1, this array. So this is dt dx, so this is really p at position 1, which is really dt dx at position 1, which is really just y1, okay? So it's going to take this array, and let's do it at this position. So y1 at x equals 0, y1, which is the first derivative at x equals 1, for example, all the way to y1 at x equals n. And the function for this is going to be minus qgen over k, okay? So that one, this is actually what we're trying to solve. This is the unique information. Qgen over k at x equals 0. This is qgen over k minus qgen over k at x equals 1, and so on until you get to minus. It's going to be an array that ends at minus qgen over k at x equals n. So at each node. And the thing is, in most cases, this could be a constant, in which case it's the same. You still need to define the function at each node. So this is the function at each node, meaning at each position. And the function can be a constant, but you need to make sure you define it. You can't just put in a constant. You need to define this constant at each node, okay? Or generation or k could vary as a function of position. You would just put the appropriate, you would evaluate k at that position, k at this position, k at this position, okay? So that's how we define the function, okay? So we're going to input all of these things. We're going to input this function. We're going to input x. And now initial guess is easy. We need to input the boundary condition, okay? So let's look at the boundary condition. So let's look at an example if you had a fixed temperature boundary condition. And in this case, we're going to say the temperature at this surface is T1, the temperature at this surface is T2. So the temperature at, node 0 is T1, the temperature at node N is T2. Okay, so that's what's written here. Temperature at node 0 is T1, temperature at node N is T2. So what is a boundary condition residual? This is a function. It wants a boundary condition function, which evaluates the residual, and the residual should be 0. So how you would convert this into a boundary function to compute the residual, it would be 0 equals t at 0 minus t1. Okay, so I'm just rearranging this. And so rearranging this, rearrange this. So the other boundary condition would be 0 equals t at node n minus t2. So these are the two functions. You would input these two functions, and it's going to try and make sure that they're always equal to 0. So set the boundary condition so it equals 0 on one side. That's how you'll get the residual. So it wants it in this solve BVP, it wants this as a function, just like we did f, had to be input x and y. Well, boundary condition, this is a function which needs to input these to arrays ya and yb, okay? So what are these Python or scipy describes how it wants these. These are going to be the position at each boundary. So this would be these two positions, okay? So take your y array, and ya is going to be at the left boundary. So this would be this ya, and it equals y of 0 at x equals 0, and then y of 1 at x equals 0. Okay, so that's going to be ya. That would be kind of the input it wants here. And you can call this, so this is just top element is ya 0 and ya a 1. Okay, that's going to be the two elements of this ya array. They're going to correspond to this. And yb is going to be at the other node. So this is yb. It's how it's distinguishing the two surfaces, where the two boundaries. We're going to define the boundary value problem. So this is going to be y at n. I'm sorry, y0 at x equals n, and y1 at x equals n. Okay. So this is going to be YB element 0, YB element 1, okay? The two elements of the YB array. So this is basically what it's taking as the inputs. It's taking the two sides of this. So what we need to do is we need to write our residual function in terms of the inputs. The inputs to this function are YA and YB. So how do we write this in terms of YA and YB, which is how it wants to format this? So boundary condition in terms of this, let's write them. So this is just going to be an array. The first one is going to be this function, so it's residual, so we know that whatever we put has to equal 0, okay? So you don't have to include this. That's what it means by residual. So T0, okay, we know that's this value. So that's going to be this value here. So you take this first element. So temperature at 0 is going to be YA0. YA0 minus T1, which is known. And then the second boundary condition is going to be temperature at N minus T2. So temperature at N is going to be this value. Okay, so on the YB array, it'll be this value, which is YB0 minus T2. Okay, so that's all you have to do to set this up. So now let's program it in Python. So we're going to come down here. Let's do an example of a fixed temperature boundary condition, okay? So there's no generation. We're going to set generation equal to 0, okay? So you get the Laplace equation, and the generation is 0. And then let's just say we have two temperatures. So the temperature at the left boundary is 0 degrees. It would be T1. Temperature at the right boundary is 100 degrees. And yeah, let's solve it. So we know the analytical solution should just be a straight line. So let's use Python to give us that. So let's input our variables here. So the first thing we need to do is import the appropriate libraries, okay? So we're going to come and we're going to import numpy. Always need numpy as np. We're going to import scipy.integrate. So that's the integrate package as intg. And this is going to be, we need to plot these things. So we're going to import matplotlib.pyplot as plt. Okay, so this is going to allow us to do basic math would be the first one, advanced math is the second one, and then plotting is the third one. So let's define this function that we just made. So let's define the equations and boundary conditions. Okay, and so we know we need to define our function of x and y. And so this is how we're going to start to define it. And so the return of this function is going to be we said it's going to be a two-part array. It's going to be an array of the y1 values and an array of minus q gen over k. So this is our function. This is what the derivatives equal. This top element is what this derivative equals. The second element is what this derivative equals. Okay, so we're going to return to set up these two. We're going to use a function called np.v stack, okay? And so this is going to allow us to put in the two elements. So the first element, and then we'll do a comma, and then a second element, okay? So inside of here, we want it to be in parentheses, okay? So the first one is going to be the array y1, okay? Y1 at each position. So this is going to be just y1, and the reason we could input that is because y is one of the inputs, so we can input this function in terms of x and y, the dependent and independent variables. So we know this one is in terms of the first element of the y array, which is this. I'm sorry, y1, second element. And the second element is going to be an array of this q gen over k. Now, this is going to be 0. We can set it up for an arbitrary generation, okay? And so to set up an array, you can use numpy. So we'll say numpy.full_like. And what this is going to do is set up a numpy array that is going to have the same length and look just like another array. So we want it to be defined at every node, okay? So let's set up our nodes first, okay? So we can come up here and let's set up our grid. So we're set up the grid. So let's say in our example problem that the length of this is going to be 1 meter. Okay, so we're going to say L equals 1 meter. And then the number of nodes Again, they just need to be enough nodes to get an accurate solution. If it looks like it's jumpy or it's not a smooth transition or inaccurate, you can add more nodes. We can just do 50. And so let's set up an array of the independent variable x, and it's np.len space. It's going to set up an array, which is a linear space between 0 and L, 0 and 1, using this many number of nodes. So nodes is what we define as 50, okay? So this is an array of all the different nodes. And so what we want to do is generate another array. So we'll say np full like, and it wants to be just like x. So it's going to look exactly like x. So whatever we make x, this is going to generate an array with the exact same number of elements. And then we want to fill it with a particular value. Okay. So we're going to fill it with minus q gen divided by k. All right. So this is our function. So we need to define these variables. So we'll come up to the top, and I like to define, we'll call it setup, the parameters. And so what we need is to define qgen, and let's say it equals 0. And then we need to define k. And in this case, in our example, let's just say 40. So k equals 40. And this is going to be, make sure you have the right units, watts per meter to the -1, Kelvin to the -1, okay? So this is watts per meter Kelvin. So this is defined, so we got our function. Now we also need to define the boundary condition. The boundary condition function. And we said this is in terms of ya and yb. Okay, so here's our boundary condition function. And what it's gonna do is return these values that we set here. So if it's a fixed temperature boundary condition, we need to define it in terms of the inputs, which are ya and yb. And this is going to be an array. So it's np array, it's just 2 values. And this array is going to be, we'll put it in terms of these brackets, ya at 0 minus t1, and then yb at 0, or the 0th element of yb minus t2. Okay, so this is exactly what we defined here. And now we just need to define T1 and T2. Okay, so T1 we're going to say is 0. This is Celsius. T2 is going to equal 100 Celsius. I'm sorry, yeah, Celsius. And then, yeah. So what we need to do is we have everything defined. And so we can set up this solve BVP, okay? And so we need to first make an initial guess to input for the temperature. So it's going to output the temperature. And the two initial, this is the output. So we're giving it a function dy dx, and it's going to solve an output y. In this case, it's 2 elements because we're giving a system of equations. So let's give it an array that looks like this. Would be an example output guess for y, and we can just fill it with zeros, or you can fill it with any value. Zeros is fine because it's not a complicated problem. Depends on your problem. Some problems depend on what you guess. It converges on different things. The problems we're looking at, not a big deal. So let's just say our initial guess, we'll call it y0. Let's just make an np array, and we'll call it zeros. Okay, so this is going to make it a zeros, and then the size is going to be, or the number of elements is 2. And the size of each one of these elements, let's make it the same as x. So this is going to define how many nodes. So we're going to say x dot size. So that's going to be how many elements to put in it. So this is the number of elements and how long they are. Basically, you know, a 2D array that's 2 dimensions, 2 rows, and the number of columns that equal the same number of columns we have in the x array. So we'll set it up as a grid. So this is it. So we can come in here and type solve. Let's define our solution is going to equal intg is the integrate library. And then the function we're going to call is solve underscore BVP. Okay. And what we need to do, it tells you input the function, boundary condition residuals, x and y, and we're not going to use these other things. Okay. So what we need to do is input the function f. We already have this defined. You don't need to give it the inputs. It's automatically looking for it to be set up as a function of x and y. BC, and it's automatically going to be looking for it to be set up with YA and YB as the inputs. We need to give it our array of the dependent variables. This is the nodes. This is X. So these are all the positions we're going to solve it at. You can change this to make it more nodes or less nodes, and you're just going to pass it so it knows which nodes to solve it at. And you need to give it a blank array of the output, a guess. So this would be Y naught. And so this is going to be 2-element array of the output. And that's it. So then that's going to solve it. And we can run it actually. So let's run this. Runs really easy. We can come into, hold on, I need to turn this. So we ran this, and now I'm going to come into the variable explorer, and this is using the Spyder IDE. So the output is called SOL. So this is the solution. It's just a BVP result, and it's got an output array Y. And so this is the Y output. Okay, so it's got X as the nodes. This is all the different positions to 0 and 1, which is the length, and then Y is going to be, oh, here, where did I lose it? Okay, so Y is going to be the two arrays. So this is solving, let me pull back exactly what we had here. So Y is outputting, this first element is going to be the temperatures at each position, okay? And the second element is going to be the first derivative at each position. Okay, so, oh, I'm realizing now that you can't see. Okay, but we will basically, let's extract these values, okay? So if we say that the temperature is going to be the first element of the Y array, so temperature equals solution, and then we'll call the variable Y element 0, okay? And then the dt dx is going to be the solution dot y element 1. Okay, so this is exactly how we defined it. So this is going to be y0 is the temperature, y1 is the first derivative. Okay, so we're just going to re-extract these out. You can pull them out, and now you can see we have the t is going to be an array that's 50 elements long, so 40 nodes. And this is going to be the temperature at each position. And then we also have dt dx, which is right here. So this is going to be the first derivative. So that's how we do this, okay? That's all there is to this. Now I'm going to give you some more tips here so we can help visualize it. We'll look at a couple more examples, but that's the gist of how you set it up and how you output your answer. But what if you want to extract some information? So let's say you wanted to look at the surface temperatures, okay? So let me scroll down here, add some extra elements. And then I'm going to say, what if you want to look at the surface temperatures? So how would you get the surface temperatures? Let's say TS1 is going to be the temperature. We know what these are, okay, because we defined them. But say you wanted to, if you had a system where you didn't define them, but how would you extract the surface temperature? It's going to be the temperature we defined as this array of the output temperature values. Element 0. That's going to be all the way to the left at node 0. And you want TS2. This is going to be temperature, and you can use -1. That's going to take node in, the very last element. In Python notation, you just type -1. So that would be how you get the surface temperatures. Let's run it and see. So look, TS1 is going to be basically 10 to the -14. That's 0, which is what we input. And this is not exactly 0 because we're doing a numerical solution. TS2 is 100, which is what we put in. That's nice. What else could you do? You could compute the flux. Okay, so how do you define flux? Q equals -k times dt dx. Okay, so if we don't define a particular value, we know dt dx at each position. But if we don't define it at each position, then we're going to give output an array. So it's going to multiply this constant k times the array dt dx and output an array q. And so let's look at this array q. So it's -4000. So this is going to be you can see it's constant. This is, oh, you can't see, sorry, it just didn't pop up. But the idea is it's this array, it's value 4000. Okay, to visualize these, we can plot them. So I can show you how to plot these real quick. And plot them, basically want to do, I just use plot. First I define the figure, so call it figure 1. I always add a little bit better resolution, DPI equals 220. Or we can say 120. DPI equals 120, so you have a good resolution. You can always define your scale, okay? So I like to use plot scale, a linear scale. You can just add these things in, plt.yscale and .xscale. I'll just define them as linear. You can define your plot limits, okay? So these, I'm gonna comment them out because it'll automatically plot everything if you don't define it, but these are good practice to put in there. So X limit between 0 and 1, Y limit between 0 and 100, for example. I'll leave them in just to show you what it looks like. I like to add a temperature, a title, and an X label and a Y label. So you can do plt.title and add temperature profile. X label is gonna be distance in meters. Y label is going to be temperature in Kelvin, okay? So, yeah, let's just change these units to Kelvin so that this is all makes sense. This is fine. Well, that doesn't work, actually. So this is because you can't have 0 Kelvin. So, yeah, let's say the temperature is in C. And now let's plot this, okay? So what we type is plt dot, this is actually the only really important one you need, plot. You need to give it the X, so if you're plotting a list of data points, you'd give it X and Y. In this case, the values are X and T. And what we can do is we can do this exact same thing. Let's plot the flux as well. So this will be figure 2. Let's do a linear scale. I don't know what the Y limits are for this one, so we'll cancel these out. But this is gonna be the, we'll call it the heat flux. And it's going to be distance in meters, and it's going to be the flux, and the units of that are going to be, because we did everything in SI units, is going to be kilowatts, and then if you want to do per meters to the -1, so you can do a $sign, and then you can do a little caret, and then put everything in brackets. So you want to make -1. You can do another $sign. So this puts it into math mode. Everything in between these two $signs is math mode. So the caret will make it superscript, and everything inside the brackets will be what's superscripted. So meters to the -1, Kelvin to the -1. Okay, so $sign, superscript, Kelvin to the -1. Okay, and a unit Celsius and a unit Kelvin is going to be the same. So when you take dt, dx, it doesn't matter if t is in Celsius or Kelvin, because 1 degree Celsius is 1 degree Kelvin when you're taking the derivative. And in this case, we're going to plot x and q. Let's plot this in kilowatts. So let's say q divided by 1,000. Okay, there you go. That's all we need. So let's run this, and let's look at the plots that come out. So the first plot that comes up is your temperature profile from 0 to 100. You see they go right to the corners because we defined the limits from 0 to 1 and from the 0 to 100. Okay, so let's get rid of these, and it's kind of nice. You can see, I'm gonna clear everything. Okay, so the first plot now, it gives you a little buffer. So, you know, it gives a little space on either side. It's kind of nice. But anyway, you can see it's a nice linear temperature profile, which is exactly what we expect from the analytical solution, but we don't need to solve it analytically. And what's the heat flux? We know the heat flux is constant in this example, and that's exactly what we see. This Q array is going to be 4 kilowatts per meter Kelvin. Okay, so look, you can see I got these nice superscripts. So anyway, that's it. Now you don't need to rewrite this. You can just use it exactly as it is, and you can just change what your function is and change what your boundary conditions are, and that's it. So let's give another quick example. If we had generation, just to prove the point. So if we had generation, what's going to happen is we could say, let's say Q equals 20, let's say kilowatts per cubic meter. So this is Q gen. This is the volumetric generation. So all we need to do is, instead of saying the d squared t dx squared equals 0, we get d squared t dx squared equals minus q gen over k, which is how we've already programmed it. And instead of putting a 0 in for q gen, we'll put actually what q gen is. We'll do the same. Fixed temperature, assume there's some temperature at the surface. We can also get an analytical solution to this. It's a parabola. So you can get this analytical solution, but if you don't want to get the analytical solution, if you want to solve it numerically, then what we could do, we don't need to change the boundary condition, but all we got to do is come back in here And let's say qgen equals 20. Now let's do 20, 0, 0, 0, because we got to put everything in the same units. So this is going to be, is why I always write my units with a little comment. So you can use the little hash mark to get a comment. This is going to be watts per meter to the -3. Okay. So I use these double carets to represent exponent to raise to the power. Okay, so let's look at this. And look, this is exactly what we see. I don't have the plot limits defined, so it's just plotting the full range. And what you see is that the temperature goes from 0 to 100, but we get our nice parabola. You could solve for where the peak is by looking at where dt dx equals 0. So you could come into your variable explorer. This is, we defined it somewhere in here. Yeah, dt dx equals 0. So you could look for the position that this equals 0, or you could do all sorts of different techniques to find this. But anyway, you have all your information here. In this case, Q is now linear as opposed to a flat line, and you see that it's negative on the left side of this peak. So everything to the left of this is going to be going out the left side. So Q is going in the negative x direction. Everything to the right of this peak is going in the positive right direction. So anyway, just an example. So you can solve for these solutions if you have different values of qgen. Now, these examples are just kind of proof of concept for analytical solutions that we know. But more importantly, how do we solve a numerical problem that we can't actually solve analytically? So I'll give you this example with radiation, okay? So with radiation, we've got the radiation boundary condition. So let's say there's no generation, but you can also add generation. Now it's getting really complicated. But you can do all sorts of different complicated things now that you know how to solve this numerically. We'll take Laplace's equation, and let's say we have a fixed temperature T1 is 0 degrees at the left boundary. So let's not say 0 degrees Celsius. Let's say 0 degrees Celsius to the left boundary. And the radiation is happening at put in an oven at 500 degrees. So just this surface is being heated by 500 degrees. We don't know what this surface temperature is. It's somewhere between 0 and 500 degrees. And we'll say the emissivity is 0.8. So, let's take a look at this. This is our left boundary condition. This is our right boundary condition. We say flux on the inside equals radiation on the outside. So all we need to do now is rewrite these boundary conditions. Okay, so we have the same function set up, our two very first order ODEs, and we've got our left boundary condition and our right boundary condition. And so now what we need to do is write this boundary condition in terms of the inputs YA and YB. Okay, so we first get this one. So to get the residual, this is going to be 0 equals T0 minus T1. Okay, so T0 is going to be this element, which is YA0. So this is going to be YA0. It's the same as before, minus T1. Now the second element is going to be right here. So we need to say this. So if you move this over to the other side, this is going to be minus, or it's going to be positive. I'm sorry. K dt dx at x equals n plus sigma epsilon t n to the fourth minus t surroundings to the fourth equals 0. Okay, so this is what we need to input as our residual function. So dt dx at x equals n. So we're talking about at x equals n, so which is this boundary, which is yb. dt dx is this element, which is yb1. So the derivative is yb1. The temperature is yb0. Temperature derivative, okay? So this is pretty straightforward. Instead of yb0, we were going to type k times yb1 plus sigma epsilon. And now we need the temperature, okay, which is yb0 to the fourth minus t surroundings to the fourth, okay? So that's now our new boundary condition. So let's input this. So all we got to do is come in here. Let's redefine our boundary conditions. The left boundary condition is the same. Now you would come and redefine your right boundary condition. So, let's redefine this. as k times yb1 plus sigma times epsilon times, and now we need to do temperatures to the fourth. So this is yb 0 to the fourth. You do the double caret or double star here to get to the fourth power, minus t surroundings to the fourth. Okay, so this is our new boundary condition, and we need to define our new variables. And so new parameters here, we've got t2 is gone. We no longer have this as a parameter, but we have epsilon is equal to, this is our emissivity, 0.8. There's no units for epsilon. T surroundings equals 500. So this is going to be C. And then we need to convert this because now we have a temperature difference. So we need to make sure everything's in Kelvin. So temperature difference, T1 minus T2 in Celsius is the same as Kelvin. But if you have T to the fourth minus T to the fourth, you need to make sure everything's in Kelvin so that this Kelvin cancels. So we're going to do 500 plus 273.15. This is going to be Celsius to Kelvin. So now it's in kelvins, which we need for the temperature subtracting to the fourth power. And we need sigma, okay? So sigma is not a parameter, it's a constant, so I like to define them separately. So we'll define constants, which don't vary, they're just universal constants. And this is going to be sigma, and this is the Stefan Boltzmann constant, which equals 5.67 times 10 to the minus 8, so E minus 8. Okay, so now we have everything defined. We've got our new boundary condition. We've got our sigma put in. Everything else is exactly the same, okay? We're going to output our surface temperature. We're going to output our flux. And yeah, let's run it here. Let me clear this. And this is what you see. So yeah, basically what you're going to see now is this is our temperature profile. I'm sorry, I was confused because there's a curve here, but that's because we have qgen. Okay, so let's make the generation 0. So now we've got the problem. Okay, and so what you see is that yeah, we've got a temperature profile. It's 0 on the left side. What is it on the right side is not so easy to tell, but we defined it. The temperature on the right side, TS2, is now output. So let's look at TS2. It's 381. Oh, sorry, you can't see this. Oh my, I'm sorry, you're not looking at any of these plots. Okay, I apologize. I'll rerun this. Now you can see the plots. So what you see is there's a linear temperature profile from 0 to some temperature. If we want to find the temperature at this surface, we defined it as right here. So this is TS2. Come in your variable explorer, you see it's 381 degrees, okay? So now we know with this radiation at this epsilon, we can get a surface temperature. That's a surface temperature you can't really easily solve numerically. So, I'm sorry, analytically. So now you can use this sort of numerical problem solver. All you need to do is take exactly what I've written here and input your boundary conditions. The function is exactly the same if this is the function you're solving. So if you're trying to look at different radiation, convection, you can add generation if you want. All you need to do is go and redefine your boundary conditions. Maybe you need to redefine the function in terms of your right coordinate system, cylindrical or spherical, excuse me. But yeah, the idea is we can output this. You can look at the heat flux is also constant in this case, which we know to be the case because all we've done is change the boundary condition, but it's still no generation. But yeah, anyway, let's plot this. For example, this is a good place where you can use y limits between 0 and this is 500 plus 273.15. This is going to be the let's put this in Kelvin. Okay, we'll say 0 to 500. I'm sorry, and we'll keep it in Celsius. So we know 0 to 500. Now we'll replot this. And now it's plotting. We know the top of this is going to be the temperature of the radiating fluid. And we can see that the surface temperature is not quite there. And for example, now we can go and we could lower epsilon. What if epsilon was 0.5? We can redo this. And now you see that the surface temperature is only 250. So the surface temperature varies with epsilon. Anyway, now you've got a numerical solution. Once you've got a data set, there's all sorts of things you can do. You can take a numerical derivative of a data set. You can find roots of the equation. These are all different videos. But here you've got something set up to use the solve BVP function. I've shown you how to set up. Okay, let me pull up my iPad here. So here, the takeaways. We've talked about how you can, instead of doing analytical solutions, you can do a numerical solution at very particular nodes, okay? By the way, I want to show you if we have a generation term, let's say this is 50, and let's go in here. And the generation is 50, so now we get some. Let's see if we can get a nice parabola going. I want to show you the importance of the nodes. So this is, we'll say 0 to 500. Let me just get a good plot here. So let me get a nice parabola. Okay, here you go. So here we've got a parabola. It looks like a continuous line because Python is drawing an interpolation between all the data points. But really, there's only 50 data points on here. So we've defined it at 50 nodes. So for example, if we define this at 5 nodes, look what happens. Now, if I do this solution, now you can see that it's actually doing a linear interpolation between 1, 2, 3, 4, 5 points. So this is really what limits it. So the more nodes you have, the more computational power it takes to solve, which is not an issue for the kind of problems we're solving right now. So, make sure you can do 1,000 nodes. This is not a problem. And so now you'd have a really smooth function defined at 1,000 different points. So this defines how close everything is together. You could go into your plot. I think actually, let me see if I type, yeah, so I just want to show you, if you go in here, let's say you had only 5 nodes, okay? You could come in here and you could add a little tick on here. Let's say in quotes, we'll put a little tick like this. This will actually show you the 5 points instead of drawing a straight line. So now, you get to see exactly what the output values are. So, you can, I mean, this tick, this little caret will make a triangle, but there's a million different things in matplotlib to make them circles or whatever. So for example, if we increase now to 50, let's see what it looks like. You can see I'm solving it at each one of these points, okay? So if you don't put this little caret, it's just going to show you kind of an interpolation between the values. Okay, so that's what we have. I'm going to, so we got a numerical solution, all these values. I showed you how to set up the function for solve BVP. So once in a very particular format of inputs of y and x, and it has to be a system of first order equations. So take your second order equation, make it first order system, and input it. So I showed you how to break it down into the right system, where f is a function of x and y. So here we've got a y, and this is just a constant. So none of these were a function of x. And it wants y. We've defined this as our system of first order equations. And of course, we defined x at just each different position. And then I showed you how to set up your boundary conditions for fixed temperature or for radiation. All you need to do is set up your boundary condition residuals in terms of these YA and YB inputs, which of course are the first and last elements of your Y array. So anyway, that's what I have. I'm going to upload all the codes in the comment, and this scripts to be able to evaluate this. I can also upload a PDF copy of what I've written down here. So I hope you enjoyed.